In the engine room of the USS Pampanito, a Below-class fleet submarine of the United States Navy, a machinist's mate named Frank Dunn stood in July 1944 between two enormous machines that looked like nothing else in the American arsenal. They were tall, taller than a man, and narrow, packed into the hull of the submarine with barely enough space to walk between them. They ran constantly when the boat was on the surface, charging the batteries that would power the electric motors when the submarine submerged. The noise was physical. Dunn had learned to shout into his shipmate's ear from 6 inches away to be heard over the combined roar of 4 of these engines running at full power. The deck plates vibrated. The air smelled of diesel exhaust and hot metal. In the Pacific summer, the temperature in the engine room routinely exceeded 130 degrees Fahrenheit. The engines were Fairbanks Morse 38D 8 1/8 opposed piston diesels. Each one produced 1,600 horsepower from 8 cylinders arranged in a vertical line. Each cylinder contained 2 pistons, one at the top, one at the bottom, moving toward each other to compress the air and away from each other when the fuel ignited. There were 2 crankshafts, one above and one below, connected by gears at the end of the block. There were no cylinder heads. There were no valves in the conventional sense. There was nothing about the engine that resembled what a Midwestern farm boy expected a diesel to look like. And Dunn, who had grown up watching his father's John Deere tractor, had spent his first 3 weeks at submarine school in New London, Connecticut, learning to operate a machine he had never imagined existed. The Pampanito was one of hundreds of American submarines powered by these engines. So were the fleet boats that patrolled the Pacific, the Gatto class, the Below class, the Tench class. So were destroyer escorts hunting U-boats in the Atlantic. So were the Wind-class icebreakers that kept the northern supply routes open. So were the emergency power generators that kept airfields functioning when bombs knocked out the electrical grid. So were the portable generators that powered field hospitals, radar stations, machine shops, and forward command posts across every battlefield in the war. The Fairbanks Morse opposed piston diesel, a strange, upright machine with 2 crankshafts and no cylinder heads, was one of the most widely used power sources of the American war effort. It was designed for submarines. It ended up everywhere. And its story begins not in a naval engineering laboratory, but in a Wisconsin factory that had spent the previous century making weighing scales. Before the war, the United States had no meaningful diesel engine industry. This is a statement that sounds false, because the United States had, by 1941, become the most mechanized nation on Earth. Trucks, tractors, and railroad locomotives were everywhere. Ships were everywhere. Factories were everywhere. Surely, all of them needed diesel engines, and surely American industry was producing them at scale. It wasn't. Not really. The vast majority of American vehicles, cars, trucks, tractors, buses, ran on gasoline. The railroad industry was still dominated by steam locomotives, with diesel-electric locomotives only beginning to replace them in the late 1930s. American ships used steam turbines, or for smaller vessels, gasoline engines. Diesel power, which had become the standard for heavy industrial and marine applications in Europe, was a niche technology in the United States, used in some ships, some stationary generators, and some mining equipment, but not a mainstream part of American manufacturing. The Europeans had embraced diesel. Germany, in particular, had a sophisticated diesel engine industry anchored by companies like MAN and Daimler-Benz, companies whose diesels powered U-boats, merchant ships, tanks, and trucks. The British had Rolls-Royce and Ricardo. The French had Hispano-Suiza. American diesel manufacturing, by comparison, was fragmented. A handful of specialty builders producing small quantities of engines for specific applications without the vertical integration or production scale that the coming war would demand. This gap mattered for one specific and urgent reason: submarines. A submarine is not an internal combustion engine with a hull wrapped around it. A submarine is a diesel-electric propulsion system with a crew attached. The diesel engines charge the batteries on the surface. The batteries power the electric motors underwater. Everything else about the submarine, the torpedoes, the periscopes, the sonar, the crew, is secondary to the power system that moves the boat through the water and keeps it operational during long patrols far from any port. The question of who would build these engines had to be answered quickly. The answer came from a company in Wisconsin that had been in business since 1823 and that had never, until very recently, built a submarine engine at all. Fairbanks Morse and Company was founded in St. Johnsbury, Vermont, by Thaddeus Fairbanks, an inventor who had opened an ironworks to manufacture two of his patented products, a cast iron plow and a heating stove. Neither made him rich. In 1829, he started a business making machinery for processing hemp, which also did not prosper. What did prosper was a patent he filed in 1832 for a platform scale, a mechanical weighing device accurate enough for commercial use and simple enough to be manufactured in quantity. The scale made the company. By the end of the 19th century, E&T Fairbanks and Company, later Fairbanks and Morse and Company, after Charles Morse became a partner, was selling scales not only across the United States, but to Europe, South America, and Imperial China. The company won 63 medals in international industrial competitions. The Fairbanks scale, the large platform scale used in grain elevators, warehouses, railroad depots, and loading docks, became an icon of 19th century American manufacturing. If you weighed something in America between 1850 and 1940, there was a good chance you did it on a Fairbanks scale. The company diversified. It acquired the Eclipse Wind Engine Company in Wisconsin and began manufacturing windmills, the tall, multi-bladed pumps that became synonymous with the American prairie. It moved into water pumps, coffee grinders, feed mills, washing machines, radios, and farm tractors. By the 1920s, Fairbanks Morse was a sprawling, diversified manufacturer, the kind of company that made everything and specialized in nothing. Its Beloit, Wisconsin factory produced an array of industrial products that had almost no common thread, except that all of them involved mechanical engineering at an industrial scale. The company began producing engines in the 1890s, initially small stationary engines for agricultural and industrial use. By the 1930s, Fairbanks Morse was manufacturing diesel engines in a variety of sizes and configurations, competing with other American diesel builders like Cooper-Bessemer, Ingersoll Rand, and Worthington. The company had a reputation for solid, unspectacular industrial engineering, engines that worked well enough for stationary and marine applications, but that were not at the technological forefront. That changed in 1934 when the company's engineers looked at a German design that would transform everything. The opposed piston engine was not a new concept in the 1930s. Engineers had experimented with the configuration since the early days of internal combustion, recognizing that two pistons moving toward each other in a single cylinder could eliminate the need for a cylinder head, the heavy, heat-absorbing casting that capped a conventional engine's combustion chamber. Without a cylinder head, there were no valves to operate. There was no valve gear to manufacture and maintain. There was less heat lost to the surrounding metal. The combustion chamber was formed entirely by the two opposing piston crowns. It was, in principle, a simpler engine. The German aircraft company Junkers had taken this principle furthest. In the late 1920s and early 1930s, Junkers developed a series of opposed piston diesel aircraft engines, the Jumo 204 and its successors, that powered experimental long-range aircraft. The Junkers diesels were mechanical masterpieces, achieving high power-to-weight ratios and remarkable fuel efficiency. They were, as aircraft engines, ultimately impractical. Their narrow power band and complex maintenance requirements made them unsuitable for military aviation. The German military ultimately abandoned diesel aircraft engines in favor of conventional radials and inlines. But the idea survived. Fairbanks Morse's engineers, studying the Junkers design, saw an application that the Germans had not fully exploited. The narrow profile of the opposed piston engine, tall and slim, with two crankshafts stacked vertically rather than splayed horizontally like a conventional V engine, was ideal for installations where width was limited and height was not. Locomotive engine bays, ship engine rooms, and, most critically, submarine pressure hulls. Fairbanks Morse engineers adapted the Junkers principle to a larger, slower-turning, more robust industrial engine. Their first opposed piston design was the Model 38A, introduced in the mid-1930s. It was a two-stroke diesel with two crankshafts connected by a gear train, later replaced by a drive chain at the end of the engine block. The cylinders were vertical. The pistons moved toward each other to compress the fuel-air mixture, which ignited at top dead center as they approached each other. The power stroke pushed both pistons outward, each one transmitting force to its own crankshaft. The intake and exhaust ports were cut into the cylinder liner itself, uncovered and covered by the moving pistons. There were no valves. There was no cylinder head. The engine had, in some respects, fewer moving parts than a conventional diesel of comparable output. In December 1934, the United States Navy ordered 8 of these engines, 4 each for the submarines USS Plunger and USS Pollock, both of the Porpoise class. The initial 38A-8 engines, with 8 cylinders and 1,200 horsepower at 720 RPM, had problems: vibration, component wear, the inevitable issues of a new and unusual engine design being pressed into naval service before it had fully matured. Fairbanks Morse went back to the drawing board and redesigned the engine, producing the 38D8, the model that would become, over the next several years, the definitive American submarine diesel. When the war came, the Navy needed submarine engines in quantities that dwarfed anything that had preceded them. The Gatto class, which began production in 1940, would ultimately comprise 77 boats. The Baleo class, which followed, would add another 120. The Tench class, at the end of the war, added 30 more. Each submarine required 4 main propulsion diesel engines plus an auxiliary diesel generator. Do the mathematics: 230 submarines, 4 main engines per boat, nearly 1,000 main engines plus hundreds of auxiliaries, all of them needed within the 4 years of American participation in the war. And those were just the submarines. The Edsall-class destroyer escorts, 85 ships built between 1942 and 1944, used Fairbanks Morse opposed piston diesels as their main propulsion, with 4 engines per ship connected through reduction gearing to 2 propeller shafts. The Wind-class icebreakers, which kept the Arctic and Antarctic supply routes open, used the same engines. Various other surface ships, tugs, patrol boats, harbor defense craft, submarine tenders, mounted Fairbanks Morse diesels in configurations ranging from single-engine installations to multi-engine power plants. Fairbanks Morse's Beloit, Wisconsin factory, the same factory that had been making pumps, windmills, washing machines, and radios, was converted to engine production at a pace that would have been considered impossible in peacetime. At the peak of wartime production, the facility was producing 1 major diesel engine per day. This was not a simple piece of machinery being assembled from stamped parts. Each engine contained thousands of precision components, crankshafts forged from high-grade steel, cylinder liners ground to micron tolerances, piston crowns cast and machined from special alloys that could withstand the thermal and mechanical stresses of submarine service. The engines were large, each one weighing over 40,000 pounds, standing over 10 feet tall, requiring overhead cranes to move and specialized fixtures to assemble. Fairbanks Morse ranked 60th among American corporations in the value of World War II military production contracts. It produced, in total, nearly 2,300 engines for the U.S. Navy's submarines and surface ships during the war, a production achievement that rivaled the more famous manufacturing accomplishments of the aviation industry. The company also trained hundreds of Navy sailors to operate and maintain the engines, establishing schools at the Beloit factory that turned Wisconsin machinists into submarine engineers. With most able-bodied men serving in the military, the factory workforce that built these engines was predominantly female. Women, drawn from the agricultural communities of southern Wisconsin, from the manufacturing towns of Illinois, from wherever labor could be found, operated the machine tools that bored the cylinder liners, ground the crankshafts, and assembled the precision components that would, in a few months, be pumping oil and breathing air inside a submarine somewhere in the Pacific. These women learned skills that required years of apprenticeship in peacetime. They learned them in weeks. The Fairbanks Morse ED-38D 8 1/8 was unlike any engine that most of the men who operated it had ever seen. Understanding how it worked, even in rough outline, requires a brief detour into mechanical principles that were, in 1941, genuinely exotic. In a conventional four-stroke diesel engine, the piston moves down to draw in air, intake stroke, up to compress it, compression stroke, down again when the fuel is injected and ignites, power stroke, and up to expel the exhaust, exhaust stroke. 4 strokes. 2 revolutions of the crankshaft per power stroke per cylinder. Valves at the top of the cylinder open and close to admit air and release exhaust. A camshaft driven by the crankshaft through gears or chain operates the valves in a precisely timed sequence. The engine is mechanically complicated. The Fairbanks Morse opposed piston diesel worked differently. It was a 2-stroke engine, 1 power stroke per revolution per cylinder, meaning twice the power density of a comparable 4-stroke. The 2 pistons in each cylinder moved toward each other during the compression stroke, squeezing the air between them. Near the point of maximum compression, diesel fuel was injected into the combustion chamber between the piston crowns. The fuel ignited spontaneously from the heat of compression. No spark plugs, no ignition system, just the physics of compressed air reaching combustion temperature. The expanding gases pushed the pistons apart, driving both crankshafts simultaneously. The intake and exhaust were handled by ports, holes cut into the cylinder liner at different heights. The upper pistons near the top of the cylinder uncovered intake ports when they reached the outer limit of their travel. The lower pistons, near the bottom, uncovered exhaust ports. A supercharger blew fresh air into the intake ports, scavenging the cylinder of exhaust gases and filling it with the fresh charge needed for the next cycle. The timing of the ports was determined by the physical geometry of the engine: no valves, no camshafts, no complicated timing gear. The engine's combustion cycle was regulated by the positions of the pistons themselves. The 2 crankshafts, one at the top, one at the bottom, were connected by a vertical drive at one end of the engine. This drive consisted of a set of helical gears that kept the 2 crankshafts in precise phase and transmitted the combined power to a single output shaft. The output went to a generator on submarine installations for charging the batteries, or to a reduction gear on surface ship installations for driving the propellers. The engine was surprisingly slender for its power output, a tall, narrow machine that fit into the confined space of a submarine pressure hull in a way that no conventional V-engine or inline engine could match. It was also, for its time, remarkably efficient. The opposed piston design eliminated the heat losses associated with cylinder heads, and the 2-stroke cycle delivered more power per unit of displacement than a 4-stroke. A 38D 8 1/8 with 16 cylinders produced 1,600 horsepower at roughly 720 RPM, slow enough that the engine could run on marine diesel fuel without the refinement required for higher-speed engines, and slow enough that the mechanical stresses on components were manageable even for an engine designed and manufactured in 1941. A submarine engine room in World War II was one of the extreme working environments in human experience. Consider the dimensions. The pressure hull of a Below-class submarine was 27 feet in diameter at its widest point, a circular tube packed with machinery, torpedoes, fuel tanks, batteries, and 90-odd men. The engine room occupied roughly 40 feet of the boat's length, divided into forward and after engine compartments, each containing 2 Fairbanks Morse diesels. The engines were arranged in pairs, separated by a narrow aisle barely wide enough for a man to walk between them. Above the engines were the overhead piping runs, seawater lines, fuel lines, exhaust lines, air lines, electrical conduits, packed into every available inch of overhead space. Below the engines were the bilges, the fuel transfer pumps, and the lower-level service spaces. When the engines ran, the compartment was in assault on every sense. The noise was not just loud, but comprehensive, a physical pressure that filled every cubic inch of airspace and vibrated the deck plates underfoot. Conversation was impossible above a shout. The men who operated the engines developed an elaborate system of hand signals and lip reading to communicate with each other. The heat was tropical even in Arctic waters and hellish in the Pacific. The engines themselves radiated enormous amounts of thermal energy, and the engine room ventilation could only do so much against 4 1,600-horsepower diesels running at full load. In the Pacific summer, with the submarine on the surface in the tropics, engine room temperatures routinely exceeded 130 degrees Fahrenheit. The men worked stripped to the waist, drinking salt tablets and water, watching each other for signs of heat exhaustion. The smells were distinctive. Diesel fuel, hot oil, the metallic tang of overheated iron, the sharp, eye-watering bite of exhaust gases that saw too many depth charge attacks and too many emergency dives. When the submarine submerged and the diesels shut down, the engine room became eerily quiet, only the whine of the electric motors and the hum of the auxiliary equipment. But the heat persisted for hours, soaking out of the engine blocks and radiating into the still air until the compartment cooled to something approaching habitable. The machinists' mates who operated the engines were the most experienced enlisted men on the boat. They had completed submarine school at New London, where they had learned the Fairbanks Morse engines on training rigs that Fairbanks Morse had supplied to the Navy for instructional purposes. They knew every valve, every seal, every gauge on the engines they operated. They could diagnose faults by sound, a change in the engine's rhythm that signaled a sticking fuel injector, a faint whine that meant a supercharger bearing was beginning to go. They carried out running repairs at sea in conditions that no shore-based mechanic would tolerate for a moment, with the knowledge that a failure they could not repair meant a submarine that could not surface, could not charge its batteries, could not come home. The watch rotations in the engine room were brutal. 4 hours on, 8 hours off, around the clock, for the duration of a patrol that might last 60 days. A machinist's mate stood his watches in the heat, reading gauges by the red combat lighting, logging fuel consumption, oil pressure, exhaust temperature, and a dozen other parameters on the engine log sheet. When the engines ran, the job was mostly vigilance, watching for the subtle signs of trouble that would let you intervene before a small problem became a serious one. When the boat submerged and the diesels shut down, the job shifted to maintenance, the endless cycle of oil changes, filter replacements, seal inspections, and fuel system priming that kept the engines ready to run again when the boat surfaced. And submarines surfaced often. The old picture of a submarine as a stealth weapon that lurks beneath the waves, surfacing only rarely, does not match the reality of World War II diesel-electric submarine operations. Because the batteries had limited capacity and the submerged speed was low, submarines spent most of their patrol time on the surface, running the diesels for propulsion and battery charging, diving only for tactical reasons, to attack, to evade, to escape. A typical fleet submarine patrol involved hundreds of hours of diesel operation for every few hours of submerged running. The engines were, in practical terms, the primary power source. The batteries were backup. The Fairbanks Morse engines went to war, and they did what they had been designed to do. American submarines in the Pacific conducted a campaign against Japanese shipping that is one of the most one-sided victories in naval history. By 1945, American submarines had sunk over 5.5 million tons of Japanese merchant shipping, more than half of Japan's pre-war merchant fleet. The Japanese economy, which depended on imported oil, iron ore, rubber, and food, was strangled by the submarine blockade in a way that parallels and in some respects exceeds what the German U-boat fleet had tried to do to Britain in the Atlantic. This campaign was possible because American submarines were available in quantity, ranged far into Japanese waters, and returned to base at the end of their patrols ready to go out again. The engines made all of this possible. A submarine with unreliable diesels was a submarine that spent too much time in port being repaired. A submarine with reliable diesels was a submarine that spent its time at sea, sinking ships. The Fairbanks Morse engines were reliable. Not perfect, no engine is perfect, but reliable enough that the submarine fleet maintained an operational tempo that the Japanese had not anticipated and could not match. Specific boats built reputations on their engine reliability. The USS Tang, commanded by Richard O'Kane, conducted 5 war patrols and sank 33 ships before being lost in October 1944, not to enemy action, but to a circular run of one of its own torpedoes. The Tang's engines never failed her. The USS Barb, commanded by Eugene Fluckey, conducted missions that included sinking a Japanese train. A shore party went ashore and planted explosives on the tracks, and earned the Medal of Honor for its commander. Fluckey's engines ran for thousands of hours of patrol duty without a major failure. The USS Wahoo, the USS Harder, the USS Silversides, the legendary boats of the submarine force, all rode on Fairbanks Morse diesel and all credited their success in part to the reliability of their power plants. There were failures. There were submarines lost with all hands, some of them perhaps to engine casualties that would never be known because the boats did not return to tell the story. There were engines that threw connecting rods through their crankcases, engines that suffered supercharger failures, engines that developed coolant leaks that could not be repaired at sea. The Fairbanks Morse diesels were not magic, but their failure rate was low enough, their reliability high enough, that the submarine commanders who operated them developed the kind of quiet confidence in their machinery that combat demands. The certainty that when you called for full power, the engines would deliver it. And when you called them to run for 20 hours straight during a long pursuit, they would run. On the surface ships, particularly the Edsall-class destroyer escorts, which hunted U-boats in the Atlantic, the engines performed similar duties under different conditions. The destroyer escorts spent long hours at sea, often in the worst weather the North Atlantic could produce, with their Fairbanks Morse diesels running continuously. The engines handled the continuous duty without complaint, driving the ships at speeds sufficient to overtake the surfaced U-boats that were their primary targets. The German submarine fleet used diesel engines too. Of course they did. Every diesel-electric submarine of the era, on every side of the war, depended on the same basic principle: diesel engines on the surface, electric motors underwater. The difference was that the German U-boats used engines built by MAN, Maschinenrie Fabrik Augsburg-Nuremberg, and other German manufacturers, not opposed piston designs. The German submarine diesels were conventional 4-stroke V engines, 2 banks of cylinders arranged in a V configuration, connected to a single crankshaft at the bottom. They were excellent engines by any reasonable standard. MAN had been building diesel engines since Rudolf Diesel himself had developed the first working prototype in the 1890s, and the company's submarine diesels reflected decades of refinement. But the German engines were not opposed piston. They were wider than the Fairbanks Morse units, and this mattered. It affected how the engines fit into the submarine's pressure hull, how they were arranged in the engine room, and how the boat's designers could allocate the space. The Type 7 U-boat, the workhorse of the German submarine fleet, was a significantly smaller boat than the American fleet submarines. Some of this difference was driven by German strategic doctrine. The Type 7 was intended for short-range patrols in the North Atlantic, not the 6,000-mile voyages that American submarines routinely made to Japanese waters. But some of it was also driven by the engines themselves. The opposed piston design allowed American designers to build larger submarines with larger engines and longer range because the narrow engine profile left more room for everything else. The Japanese had their own submarine diesels, produced by various domestic manufacturers. The Japanese submarine fleet was, by 1945, essentially destroyed, not primarily because of engine problems, but because Japanese strategic doctrine never committed fully to commerce rating the way the German and American fleets did, and because Japanese submarines faced an overwhelming anti-submarine campaign that their technology and tactics could not counter. But the Japanese diesels were also, technically, less refined than the American or German engines. Japan did not have the industrial base to produce diesel engines of the precision and reliability that modern submarine warfare demanded. Its submarine fleet suffered accordingly. The opposed piston design was, in the end, a uniquely American solution to the submarine power problem, a solution that combined German mechanical ingenuity, the Junkers concept, with American industrial scale, Fairbanks Morse's mass production capability. Other nations could have adopted the design. They didn't. The design remained distinctively American, and it gave American submarines advantages that the boats of other nations could not match. The Fairbanks Morse engines did not stay on submarines. They spread across every theater and every service of the American military, finding applications that their designers had not anticipated. Emergency power generation was one of the largest categories. The Army Air Forces established hundreds of airfields around the world, many in locations where no electrical grid existed. Each airfield needed reliable power for lighting, radar, communications, fuel pumps, and maintenance facilities. Fairbanks Morse opposed piston diesels in smaller configurations than the submarine engines, but built on the same basic architecture, were shipped in large numbers to forward airfields as primary power generators. The engines were packaged in mobile units, mounted on trailers or in prefabricated buildings, and delivered to locations that would have been utterly without electricity if they had not arrived. Field hospitals used them. Forward radar stations used them. Maintenance depots for aircraft used them. Ammunition storage facilities used them to power refrigeration and ventilation systems. The Fairbanks Morse diesel became, in its smaller industrial configurations, the universal power source of the American military, the thing that ran when nothing else could run, the thing that turned the lights on in places where there had been no lights before. The Navy used them on surface ships in roles beyond main propulsion. Essex-class aircraft carriers carried Fairbanks Morse diesels as backup generators, capable of providing emergency power if the ship's steam plant was damaged in combat. Fleet oilers, ammunition ships, and repair ships used them as auxiliary power sources. Submarine tenders used them for both power generation and to power the compressors and pumps that serviced the submarines alongside. On land, the engines powered military bases, factory backup systems, and critical infrastructure that the war effort could not afford to have go dark. When the German bombing campaign disrupted British power supplies in 1940 and 1941, American Lend-Lease shipments included Fairbanks Morse diesel generators that kept essential British industries running during the worst of the Blitz. The engine that had been designed for submarines became the American military's universal solution to the question of how to produce electricity or mechanical power reliably in portable form anywhere on Earth. It was not the most efficient diesel ever built. It was not the most powerful, but it was the one that Fairbanks Morse could build in quantity, that the Navy trained men to operate, and that the military infrastructure was organized around. The ubiquity of the Fairbanks Morse design mattered more than any single technical advantage. The engine was everywhere, so parts were everywhere. So mechanics who knew how to fix it were everywhere. Once an industrial standard establishes itself, it tends to stay established, and the Fairbanks Morse opposed piston diesel became a standard because it was there first, in sufficient numbers, with enough training infrastructure to support it. After the war, the Fairbanks Morse opposed piston diesel found new lives and new applications. The submarine fleet continued to use the engines. When the post-war pancake engines developed for the Tang-class submarines proved unworkable, they were an ambitious but ultimately failed attempt at a more compact diesel. The Navy reverted to the wartime Fairbanks Morse design, which remained the standard for American diesel-electric submarines through the early 1960s. Even after nuclear propulsion replaced diesel for primary submarine power, Fairbanks Morse diesels continued to serve as emergency backup generators on nuclear submarines through the Seawolf class of the 1990s. Every American submariner trained between 1940 and 2000 had at least passing familiarity with the opposed piston design. The engine migrated to commercial applications. In the late 1940s, Fairbanks Morse attempted to enter the diesel locomotive market, using the 38D 8 1/8 in a series of mainline freight locomotives. The attempt was not fully successful. The engines that had thrived in submarine service, where they ran at moderate load with plenty of cooling water, struggled in locomotive service, where loads were higher, cooling was more difficult, and maintenance was less intensive. Fairbanks Morse ultimately exited the locomotive market in 1963, but the engine continued to serve in marine applications, as stationary generators, and as the backbone of various industrial installations around the world. And it is still in production. The 38D 8 1/8, essentially unchanged in its fundamental design since 1938, is manufactured today by Fairbanks Morse Defense in Beloit, Wisconsin, the same factory, though expanded and modernized, where the wartime engines were built. The company that had begun in 1823 making weighing scales still exists, still makes opposed piston diesels, still supplies engines to the United States Navy. Modern Fairbanks Morse engines power backup generators on nuclear submarines, drive propulsion on Coast Guard cutters, and serve in various civilian marine and industrial applications around the world. Few pieces of World War II military technology have had this kind of longevity. The B-17 is gone. The Sherman tank is gone. The Fairbanks Morse opposed piston diesel, refined and updated, but recognizably the same machine that powered the Pampanito's engine room in 1944, is still running. The reason for its survival is the same reason it worked so well during the war. It is a simple engine. It has fewer moving parts than comparable conventional diesels. It is physically compact in one dimension, width, at the cost of height, an acceptable trade-off in most of its applications. It is forgiving of abuse, tolerant of imperfect maintenance, capable of running for extraordinary periods without major overhaul. It was designed for submarines, which demanded the most extreme combination of reliability and power density of any contemporary application. It was adapted for everything else because the submarine requirements forced a level of engineering excellence that made the resulting engine suitable for almost any heavy-duty application imaginable. The men who built it, the women, really, for most of the wartime workforce, worked in a factory in Wisconsin that had been making scales and windmills and washing machines a decade earlier. They learned new skills quickly, under pressure, because the war would not wait. They produced nearly 2,300 engines between 1940 and 1945 at a peak rate of 1 major diesel per day, and delivered them to a Navy that used them to power the submarine campaign that choked Japan into submission. If you visit the USS Pampanito today, she is a museum ship moored at Pier 45 in San Francisco. You can walk through the forward engine room and see the Fairbanks Morse 38D 8 1/8 diesels still mounted in their original positions. The engines are quiet now. The pistons do not move. The crankshafts do not turn. The blowers do not whirl. But the engines are still there. The same engines that powered the Pampanito through 6 war patrols in the Pacific, that charged the batteries during the long submerged hours off a Japanese coast, that brought the boat and her crew home at the end of each patrol. Stand between them, as Frank Dunn did 80 years ago. Imagine the noise, the heat, the vibration, the smell of hot oil and diesel exhaust. Imagine the confidence that had to exist, the confidence of a 22-year-old machinist mate in the machines he operated for a submarine to function at all. Imagine all of that packed into a space smaller than most suburban garages, running for weeks at a time, 2,000 miles from any port. That was the Fairbanks Morse opposed piston diesel at war. A strange, upright machine with 2 crankshafts and no cylinder heads, designed by a scale company in Wisconsin, adapted from an aircraft engine, built by women whose brothers and husbands were fighting in the places where the engines would ultimately serve. An engine that was everywhere, that did everything, that nobody outside the Navy and a handful of industrial customers had ever heard of, and that won a submarine war nobody quite remembers in the details anymore. The engines are still running. The company is still there. The scale of the accomplishment, 2,300 engines, 200 submarines, a blockade that strangled an empire, is the kind of thing that American industry used to do, that American industry perhaps cannot do anymore, and that nobody in 1941 would have believed possible. A scale company in Wisconsin, opposed pistons, 2 crankshafts, 1 per day, for 4 years. That is how the American submarine fleet got its engines, and that is how the war in the Pacific was won, as much as it was by any other single thing, with the help of an engine that shouldn't have existed, built by a company that shouldn't have been in the business, powering a submarine fleet that should not have been able to reach across an entire ocean. It all worked. The engines ran. The boats came home. Most of them. most of the time. And the company that had been weighing grain in 1823 was still 120 years later building the heart of the American submarine force.